Okay, anybody have any homework questions for thermo?
I don't think we have homework. Or I just love.
Yeah. Lucky. Okay, well, we'll fix that today. So the next thing we have to talk about is property tables and interpolation. So remember when, yes?
Will this be on the exam?
On the exam is next Monday, right? Oh yeah, let's talk about the exam. Okay, so exam 1, next Monday.
Both classes have an exam on Monday or just?
No, statics on Friday.
Okay.
So exam 1 is Monday, 9/18.
I have a chem exam.
That sucks. Well, actually, if you're interested, let me know and we can work something out. You could take it in different day. Yeah. So the topics for this. Let's go everything up through differential first law. So this new stuff is not going to be on the test. So including the stuff we did on Friday, remember we started talking about simple compressible substances. None of that's going to be on there. All right, so last time, I introduced simple compressible substances. And remember that, so the relationships between different properties in a simple compressible substance come from the PVT surface. So remember looking at that thing? And the PVT surface had a feature called the vapor dome. So this thing is called the vapor dome. And it looks roughly like that from a few different projections. And this had a critical point up here that basically, mainly we're going to stay below the critical pressure and critical temperature. So that's not too much of a concern to us. Over here, we had a saturated liquid. So anywhere along that line, we have liquid that if you add any more energy to it, it's going to turn to gas, okay, without the temperature changing. On this side, we have a saturated vapor. Okay, saturated vapor. To the left of the saturated liquid, we had compressed liquid. Inside the vapor dome, we have a liquid vapor mixture. And to the right of the vapor dome, we have a superheated vapor. And remember that So it's important to remember this stuff. And just, if you look at that vapor dome, remember what those 1, 2, 3, 4, 5 regions represent, okay? Because this saturation thing is going to be important. One of the reasons that saturation is important is, remember, if a substance is not at saturation,
Whoa. What controls you?
So that chart varies based on, I'm assuming, the intermolecular forces of whatever fluid you're using.
say that again?
The saturation points are essentially, there's enough internal energy that it's breaking the intermolecular forces and that's going to become the gas.
Oh, yes, that's right. Yep. Good Lord, what is going on here? I lost a couple things. Okay, this is the saturated liquid over here. This is the saturated vapor. For a simple compressible substance, that's not at a saturation, not in a saturation region, two properties are required to specify all the other properties. For a simple compressible substance at a saturation, on a saturation region, how many properties do you need to specify all the rest of the properties? Just one, right? And that's going to be a really key thing. So only one property is required. And we're going to use this fact with property tables. Okay, so property tables. These give us relationships between properties for specific materials. And there are three types of tables that we're going to use. The first one is saturation tables. We're going to use these for saturated liquids and saturated vapors. So these can be indexed by pressure or temperature. These are easier to use. Because you're just using one single property to look up, your value. Then the second type is a compressed liquid table. And for this, you have to look it up using two lookup variables, indexed by both pressure and temperature. And then the last one is a superheated vapor table. And again, this is going to be indexed by pressure and temperature. Both pressure and temperature. So let's go to D2L for a second and look at what these look like. So if you go to content, one of the sections in content is just tables. And these are just tables for the materials that we're going to be using on homework problems and stuff. So let's first look up water at saturation indexed by temperature. Okay. This just says saturation. Water. So the saturation that we're interested in is the two sides of that vapor dome. So a saturated liquid that's at the boiling point, and a saturated vapor that's at the boiling point. And this table shows you values. So if we want to know what the specific entropy is of saturated liquid water at 15 degrees Celsius, okay, we'd find specific entropy over here. We'd go to the line, go across. This is the value for a saturated liquid, okay? If we wanted the saturated vapor, We go to this.
Mhm.
Okay. So you look up the temperature and find the thing. A difficulty with tables, a problem with tables, is you can't get continuous lookup values from a table, you know?
Yeah.
And so what are you going to do if you're looking for, you know, you're not looking for 15 degrees, you're looking for 15.4 degrees. We're going to use linear interpolation for that. And I think it's useful to do this linear interpolation stuff because the principles of linear interpolation are really key things in a lot of areas of numerical engineering analysis. So even though really you would use a computer program now to look this stuff up, you just enter in your value of temperature or pressure and it would tell you the value. I think this interpolation thing is a useful thing to get a glimpse at, and you're going to see it a lot when you go to numerical analysis classes and stuff. Okay, so that is how to look stuff up, you know, for water, for saturation. So now, but that's the easy one, right? Because that's where you're looking it up based on one specific value. Like, what does it look like to look things up in a table based on two different property values? So let's go to, this is now compressed liquid water. And basically, it's just a bunch of mini tables. So you find, like in this case, you find the pressure range that you want. Say you're looking at 100 bar of pressure. Now you have this mini table. So go to the temperature that you want. Say you want 140 degrees Celsius. Go across, and this will give you your values. Okay. Anybody have any questions about the organization of these tables? Little by little, you'll be getting used to using these.
So question.
Yeah.
So, cause let's say they're not continuous, are we gonna have, like, are most of the problems gonna be, have one variable that's in between, or we have?
I'll show you how to do two variable linear interpolation, and you will have to be able to do that. But once you've done that for a while, I'm going to mostly be just using values that are in the table. You know what I mean? Because it just takes a long time.
Okay.
Any other questions? Okay, so let's get into linear interpolation, because you really can't use these tables without being able to do some kind of interpolation. So let's say that you have, we're going to first do it with just a single variable. So on the vertical axis, let's say we have our dependent variable. And on our horizontal axis, we have our independent variable. And there's the function. And let's say this is our value x1 and this is our value x2. You can imagine these are the 2 points in a table that you're able to look up. So it tells you that at x1 you have this function value here, at x2 you have this function value here, but you don't want the value of x at the two that are given. You want the value of x at some third point in between those two. Okay? This is the point that you want. Well, in order to do that, you imagine that the function between x1 and x2 is linear. And based on that linear function, you calculate the value of the value on that line at that point. That's that blue dot. And you can see, I mean, based on this, that that approximate value of that blue dot. So we want this at x. But the value of that blue dot is a closer approximation of f at the independent variable x than either the two function values x1 or x2 give us, you know. So that's the idea that we're using here. And so this approximation, the function value at x is equal to the function value at x1 plus f of x2 minus f of x1 divided by x2 minus x1 times x minus x1. So notice that this is the slope of the line. Between x1 and x2. Bless you. Okay, and so if you follow this equation, the way it works is our approximate value, the blue value, is f of x1, so this, plus the slope of the blue line times the distance here. Okay, so we're going to start at this point, and then we're going to follow the slope of the line to the x value we want. That's the idea of linear interpolation.
Is that sort of like a weighted average?
Yes,
Okay.
exactly.
So, instead of doing y2 minus y1, we're gonna take the integration of x2 and x1.
Well, you can think of those as y's, you know, I mean, those are the y values. But notice that this term here just gives you the slope of that blue line, you know. And yeah, so I mean, it's basically like all numerical techniques are based on taking the idea of calculus and just implementing them over very small intervals. And that's what we're doing here. I mean, that's a derivative, but it's finite, you know. And if you bring those points close enough together, all this stuff approaches being perfectly accurate.
That's how computers figure it out, right?
What?
That's all computers do.
Yes, that's right. That's right. And if you take your mesh or take your x1 and x2 really close together, then you can get as accurate as you want by making them closer together. Okay, so let's do an example of this. So this is a 1D interpolation. Okay, this is the approach you would use with a saturation table. So let me do an example. So let's use linear interpolation to approximate f of x equals x squared at x equals 2. Okay. And so let's say what we're given is that F at 1.5 is 2.25, and F at 2.5 is that 6.25? That is, right? Okay, so why do you have to approximate the value of x squared at x equals 2? Just plug it in, But the idea is that with the property tables, we won't know the mathematical function. Okay, so all we're going to have to go on is essentially the function value at 1.5, the function value at 2.5. Okay, so that's what we're going to be doing. And so using this linear approximation, we want to see how close we get to an approximate value being 4. Okay. All right, so to approximate F at 2, we're going to go F at 1.5 plus the quantity F at 2.5 minus F at 1.5 divided by 2.5 minus 1.5. And then that fraction is going to be multiplied by our x, the one we want, 2 minus 1.5. And so this is 2.25 plus 6.25 minus 2.25 divided by 2.5 minus 1.5 times 2 minus 1.5. And so we get 2.25 plus 4 over 1 times 0.5. And so we get 4.25. Okay. Not perfect, but a lot better than either of those two endpoints would have been at approximating it. And what would happen if we did it instead based on F at 1.9 and F at 2.1? In general, not in general, I guess, but most of the time you can expect that to be a better approximation. And in the limit, as you go to that shrinking down, it has to approach the right value. So the smaller your intervals are, the better off you are. Using these tables, you don't get any choice about how close your values are. You just have to use what's in the table. But this is the idea. So this is 1D linear interpolation. And this is the approach that you'll use for saturation tables.
Could you use it for 2D or for the other non-saturation tables if pressure stayed the same or temperature stayed the same?
Yes, right. Yes, you definitely can do that. Yep. Then, yeah. And we're going to be able to use basically the same approach for 2D also. It's just going to be a multi-step thing. Okay, let's do an example now using values that you get from the table. So at a temperature of 63 degrees Celsius, what are the pressure and the specific internal energy for, let's do this for two different things. So first, for a saturated water vapor, and second, for a saturated liquid water. Okay, so 63 degrees Celsius. The chances of that being in the table are low, you know? But, you know, maybe we'll have 60 and 65 or something. Let's see, what do we have? 60 and 65. So let's go to the table and find this stuff. So we'll go into the tables. So the first thing we have to do is find the right table. We're looking for saturation for water. And there are two of them. They can be indexed by temperature or pressure. The question we're asked for has it in terms of temperature. So that's the one we're going to use, indexed by temperature. And that'll allow us to look up the pressure. Okay, so I have to go to the second page, but here's a temperature of 60 Celsius and here's 65 Celsius. So those are the ones we want. We want pressure and we want specific internal energy. Pressure is the second column here, so that's easy to find. So we have 0.1994. This is in bar. Okay, so remember 1 bar is times 10 to the 5th. And so there is going to be some unit conversion that you have to do. If you're going to use this in the first law, you probably want to go to SI units. So you got to be careful that you get everything in SI units. But all right, we have 0.1994 bar, 0.2503 bar. Then go to internal energy. Everything in these tables is specific values, not extrinsic values, because we don't know the amount of the material we're talking about. Go over here at 60. So for the saturated liquid water, we have 251.11 kilojoules per kilogram. For the saturated vapor water at 60, we have 2456. The units are all listed above. By the way, I'll say this again when we use this in calculations, but this is the specific volume is really, really a pain the way they have it written. The value they have, so look at what this says is specific volume times 10 to the third. And so you don't take this number and multiply it times 10 to the third. The number that they give you here is times 10 to the third of the real value. Are you with me on that? So you have to multiply this times 10 to the minus third to make it the right value. It's just a weird way to sort of express it, but that's what they mean. One other thing to notice just while we're here for the first time, look at the huge difference in specific volume as you go from a liquid to a gas at the same saturation point. It's multiplied by over 1,000 times. Okay, so taking the liquid and moving those molecules apart increases the volume a huge, huge amount. And then the second thing to notice is the internal energy. You know, we talked about latent heat. We talked about how much more energy you need to put into something to take it from a liquid to a gas. Look at the huge increases in internal energy for a single a single saturation. All that energy has to be added to make the liquid separate into the gas.
But this is just taking it right at the edge of that vapor dome or whatever.
Yes, right. This is the blue and green lines on the vapor dome. Okay, so now from there we get all these values, and here's what they are. So in the temperature saturation table for water, at 60 degrees, okay, so we're going to do the vapor first. So at 60 degrees Celsius, we have a pressure of 0.1994 bar and a specific internal energy of 2456.6 kilojoules per kilogram. And then at 65 degrees Celsius, we have a pressure of 0.2503 bar and a specific internal energy of 2463.1 kilojoules per kilogram. And so we'll first do the pressure. So the pressure at 63 degrees is about equal to the pressure at 60. Plus the pressure at 65 minus the pressure at 60. Divided by 65 minus 60. And then multiplied by just the distance from the x you want to the left x value. So multiplied by 63 minus 60. And you get an approximate value of 0.2299 bar. Then the specific internal energy is the one at 60, 2456. Plus the quantity 2463.1 minus 2456.6. Divided by 65 minus 60, multiplied by 63 minus 60. And so we get an approximate value of 2460.5 kilojoules per kilogram. Okay, so for part B, let's just do one with the liquid. I don't think we have to do both of those, but so now this is for a saturated liquid. And so you have to look in a different column of the table for the saturated liquid versus the saturated vapor. Okay, and what we get for this is At 60 degrees Celsius, we have a specific internal energy of 251.11 kilojoules per kilogram. At 65 degrees Celsius, we have 272.02 kilojoules per kilogram. And so at 63 degrees, we're going to approximate this as 251.11 plus the quantity 272.02 minus 251.11 divided by 65 minus 60 times 63 minus 60. And you get an approximate value of 263.66 kilojoules per kilogram. Anybody have any questions about that? Okay, well, I have a couple of problems I can give you using the table on these, and then next time we'll get into two-dimensional linear interpolation. So, next time, 2D linear interpolation. And remember this week, think about any questions you have on stuff related to the exam. I'd be happy to answer homework questions or anything like that at the start of every class. But if people don't have questions on stuff up through the differential first law, I'm just going to keep going with this. Okay, that's all.